start the recording and share Professor Price's slides. Switch into the presentation mode.
And
we're good.
Hide the
hide the thing. And hopefully we're good to go.
Great, thank you. So welcome back everybody, both here in Bonn and on Zoom for the Bonn History and Philosophy of Physics seminar. Our speaker today is Hugh Price. Hugh had a long and distinguished career. I'm just going to mention he was the founding director of the Centre for Time at the University of Sydney, and then after many years there switched to the University of Cambridge, where he held the Bertrand Russell Chair, and now he's currently a senior professor here at the University of Bonn at the Centre of Science and Thought. Thank you very much for coming here.
Thank you very much, Dennis. It's very nice to be here, and it's very nice to be back in Bonn for the summer. This talk is in 3 parts. There's 2 short historical parts at the beginning and the end, and the main stuff is in section 2 in the beginning. But let's start with a little bit of history, which will be probably familiar to everyone in the room, maybe everyone on Zoom too. What is entanglement? Well, according to Lenny Susskind here, it's the essential feature of quantum mechanics. Susskind also says, he characterizes it this way, he says one can know everything about a system and nothing about its individual parts. The term comes from Schrodinger in 1935. Schrodinger puts it like this, as you see, it's the same idea. When 2 separated bodies that are each maximum known come to interact and then separate again, such an entanglement of knowledge often happens. An entanglement of knowledge such you can know everything about the combined system, but nothing about its individual parts. Schrodinger said it was not one, but the characteristic trait of quantum mechanics. More recently, Steve Weinberg says it's perhaps the weirdest feature of quantum mechanics. So whatever it is, it's something which is universally agreed to be weird. When Schrodinger wrote about it in 1935, he was responding to a famous paper by Einstein, Podolsky, and Rosen earlier the same year. And in his paper, he repeats an argument that Einstein, Podolsky, and Rosen had made in their paper, which goes something like this. It was an objection to the Copenhagen interpretation. So EPR and Schrodinger argued that quantum entanglement implies that something is hidden inside quantum systems, something not given to us by the ordinary quantum description and something disallowed by Bohr's interpretation. They argued that since measuring a nearby particle, A, teaches us a new fact about a remote particle, B, that new fact must have existed already, although the quantum description didn't include it. The alternative would be that the nearby measurement was changing the distant particle in some way. And Einstein, Podolsky, and Rosen and Schrodinger agreed that that was absurd. As Schrodinger puts it, measurements on separated systems cannot affect one another. That would be magic. Well, Schrodinger died in Vienna in 1961. And just 3 years later, John Stuart Bell showed, and I'm paraphrasing a little, that if quantum mechanics is correct, then Schrodinger's magic actually happens. His argument goes like this. He argued that the EPR Schrodinger view, the view that there were pre-existing properties responsible for the measurement results in those sorts of cases, that view implies that the measurement correlations satisfy what we now call Bell inequalities. But he realized that quantum mechanics predicts violations of Bell inequalities in certain cases. There are the Bell inequalities, the first line up here. So the Einstein-Schrodinger view implied that the expression that we can't see on the left here is less than or equal to 2, whereas in a particular case, quantum mechanics will predict that it's 2√2. So if quantum mechanics is correct, Schrodinger's non-local magic must actually happen. But is quantum mechanics correct? That question took a long time to answer, but we now have a ruling on the issue from a rather authoritative source, namely the Nobel Prize Committee, who last year said, in effect, the quantum predictions are correct, and gave the last year's Nobel Prize in Physics to these three people, Alan Aspect, John Clauser, and Anton Zeilinger, for, as you can see there, experiments with entangled photons establishing the violation of the Bell inequalities. So there's the Stockholm mandate for this claim. Whereas Aspect himself put it in his speech on behalf of the three of them at the Nobel Prize banquet, he says entanglement is confirmed in its strangest aspects. So there's no doubt about the reality of it these days. One of these strangest aspects is the apparent conflict between entanglement and special relativity. Here's a quote from Bell from the mid-1980s. Bell says, "For me, then, this is the real problem with quantum theory, the apparently essential conflict between any sharp formulation and fundamental relativity. That is to say, we have an apparent incompatibility at the deepest level between the two fundamental pillars of contemporary theory." Now, of course, already by that time, and since that time, many people have put effort into trying to show that that apparent tension is less serious than one might think or can be dealt with in some way. But here's a judgment from only 10 years ago, a piece by David Albert and Rivka Galchin in Scientific American. They say non-locality poses a threat as yet unresolved to special relativity, a foundation stone of our 20th century physics. So I think it's correct to say that it's still true that one of the strangest features of entanglement is this apparent conflict with relativity. Okay, so much for history. Now to the main part of the talk. We know that the world is like this. The Nobel Prize winning experiments have confirmed it to everyone's satisfaction. But why is it like that? What is entanglement? Where does it come from? Why should the quantum world behave in that strange way? We've got a proposal. A simple proposal, really, because it's a proposal that entanglement is a natural result of combining just 4 simple ingredients, all of them already available off the shelf, although in one case, admittedly, a very remote corner of the shelf, and most people wouldn't think of looking. Not these ingredients exactly, but as you'll see, quite simple ingredients. The first ingredient comes from causal modeling, study of the abstract structure of causal relationships. In the terminology of causal modeling, a collider is an event or a variable with more than one contributing cause. So it's depicted in causal diagrams by 2 converging arrows like that. That's why it's called a collider, because it's a point at which 2 arrows collide. Now, it's a very well-known fact that if we restrict our attention to or condition on, as causal modelers say, the cases in which a particular event happens at the collider, we often find a correlation between the causes A and B, even though in fact they're independent. And this can look like a causal correlation, but it's a causal artifact, as causal modelers say, the result of selection bias or collider bias. The mistake of interpreting this correlation as if it were a genuine causal connection has a name. It's often called Bergson's fallacy. And here's an example of Bergson's fallacy. It's not my favorite example, but I can't resist using it because in this article in Slate in 2014, you see the picture they've chosen which is supposed to be relevant to this question as to why handsome men are jerks. You see, they've chosen a young man from Sydney, and there's someone, that's my hometown, so I couldn't resist using this example. This example works like this. If you imagine somebody who dates men and chooses men to date according to two criteria. This person dates men who are particularly nice or particularly handsome. If you just look at the class of men who are considered eligible partners by this person, the ones who are not handsome will be nice, and the ones who are not nice will be handsome. So there'll be a correlation between the two factors. But of course, it's not a causal correlation. And as the article says, if you try to improve your boyfriend's complexion by training him to be mean, then you've fallen victim to Bergson's fallacy. Bergson's fallacy is actually named after this man, Joseph Bergson, who was a Mayo Clinic physician and statistician in the mid-20th century. His very well cited article on this is from 1946. It's this one. But as he says at the bottom, he had the idea already in the 1930s. But when I started writing about this, one of my friends said, surely somebody thought of it before Bergson. So I tried to track it down. So it's a little aside, but this is what I call the Bergson fallacy, or the question, why does Bergson get the credit for this? I consulted a person who has a reputation for the world's leading expert on collider bias. He's a statistician called George Davey Smith in Bristol. And he tells me that as far as he knows, the person who was really first to identify it was this man. This is a Cambridge economist called A.C. Pagoo. He was an economist at King's College in Cambridge. He apparently has a reputation for being the first serious optimist. I don't know what that's all about. You can see that he's serious. I don't know if you can tell that he's optimistic underneath. But in any case, as Davey Smith told me, Pagoo wrote about what we now call Bergson's bias already in 1911. Unfortunately, he published it in what's now regarded as a rather obscure place, namely a newspaper called the Westminster Gazette in London. This is the front page of the Westminster Gazette from early February 1911. The main article here is an editorial in support of the King's victory in a libel case. The previous day, there was somebody who'd accused the King of being a bigamist. This has some topical relevance given that the coronation is coming up this weekend. But after that, the next story, the next item here is this article by Pagoo called Alcoholism and Heredity. The question he's interested in is whether discouraging parents from being alcoholics improves various sorts of outcomes for children. There was apparently a lively debate about that at the time, a debate in which people were claiming that various statistics didn't show any such effect. And what what Pagoo is pointing out is that the absence of a correlation in the particular statistical samples might itself be a manifestation of what we now call collider bias, because collider bias can hide real correlations as well as we're producing fake correlation. Okay, so this is the person who we should be calling it Pagoo's fallacy. There's lots of fascinating things on this page, but we don't have time to study more of them. I just want to point out one which is particularly appealing from my point of view. See that down in the bottom left-hand corner, we have an advertisement from some new novels, and one of them is by a Welsh author called Daisy Hugh Price. I didn't know until I looked at this that I had this possible relative who was a novelist in the early 20th century. Okay, so that's Pagoo. I want a different example of collider bias, one which will be easier to exhibit the kind of structure we find in quantum mechanics. And so this is an example involving the familiar game of rock, paper, scissors. You know how this works. Alice and Bob play rock, paper, scissors, sending their choices to Colette. Is there anybody here who doesn't know about rock, paper, scissors? Good. But Colette doesn't like Bob, so she throws away all the results and Bob wins. So if Alice just sees the official results, the ones that Colette keeps, it looks to her as though she can influence Bob's choice. Similarly for Bob, although of course less happily.
You can see how it works. If you stand with your back,
But there's no causation from Alice to Bob or vice versa.
otherwise it follows the speaker around.
That's just selection bias.
And we're using the white noise for some parts.
And we can express the lack of causation in terms of counterfactuals. So suppose Alice chooses rock and wins, and Bob chooses scissors. Is Alice correct to say, if I'd chosen paper, Bob would have to have chosen rock? Well, obviously not. No, what she should say, if she knew the truth of what was going on, was if I'd chosen paper, Bob would still have chosen scissors, and Colette would have thrown away the result. So the true counterfactuals here exhibit the fact that there's no causal correlation.
Within the history and history.
Okay, now to our second ingredient. I can explain in terms of.
Thank you, and sorry.
Okay, so the first ingredient was selection bias or collider bias. Second ingredient, and this is the one which you have to look onto a remote corner of the shelf to find on the shelf. I don't think it has a name, an existing name, but Ken and I call it constraining a collider. So now imagine that God or fate or Lady Luck or your favorite supernatural being takes Alice's side in this game and makes it the case that Alice simply never loses to Bob. So it's like a law of nature, or you might call it supernature. If you don't like these, if you don't like God or fate or luck, then you could imagine that we're living in a simulation, as some people believe, produced by some superintelligence. Just imagine that that superintelligence has preferences, and can obviously has a lot of control over what happens in the game. Perhaps that superintelligence likes Alice more than Bob and makes it the case that she never loses. We call that constraining a collider because it amounts to fixing the value of the variable at that point. So in this case, fixing the value of the variable up there to Alice wins. In this case, is Alice correct to say, if I'd chosen paper, Bob would have to have chosen rock and I would still have won? Well, here, yes, because nature or supernature or the AGI or whatever it is simply doesn't allow anything else to happen. So in this strange case with a constrained collider, we get something that looks a lot like real causation across the collider from one side to the other. We call that connection across a constrained collider, or CCC. We're deliberately using a neutral term, connection rather than causation, because we want to leave it open the possibility that somebody might want to argue that that's not real causation. It looks like causation, but in some sense it isn't. We don't want to take a stand one way or another on that. We just want to choose neutral terminology at the beginning in order to avoid taking a stand on it. Now, in this simple case, one reason for skepticism about whether it should really count as causation is that it works both ways, of course, and seems incompatible with allowing that both Alice and Bob have a free choice in the matter. I mean, that's an artifact of this particularly simple case, as we'll see, and when we have a more complicated case, we can get rid of it. Okay, now I said that this could be found on the shelf if you know where to look, and this is where you need to look. So this is something called the Horowitz-Maldacena proposal. And the diagram comes from a piece by Seth Lloyd and Bergson in 2014. Does anyone here know what the Horowitz-Maldacena proposal is? Anyone come across it? I thought there might be somebody in this group. So it's a proposal for solving the so-called black hole information paradox. You probably heard of this issue, which arose especially for Hawking. Once he discovered Hawking radiation, he initially thought it was completely random, and so wouldn't carry any of the information that fell into the black hole in the first place. Now, Hawking radiation is a process whereby black holes eventually evaporate away to nothing. And that was thought to be a big conflict with general relativity. And so various people were looking for ways of avoiding that result. And this proposal was by Horowitz and Maldacena. And it works like this. See, there's information falling into a black hole. So that might be it. That M might represent, say, a motor power or something like that, something with structure falls into the black hole. Up here, we have, for people on Zoom, up here means where we get this branching labeled in and out on the diagram. In is so that branch represents particle pair creation in Hawking radiation. One member of the particle pair falls into the black hole, the other radiates away, taking away some of the energy of the black hole. What Horowitz and Maldacena propose is that at the final boundary condition inside the black hole, those infalling particles meet the information which has fallen into the black hole in the first place. And in effect, the final boundary condition acts like a measurement whose result is fixed. So it can only take one of what would otherwise be various possible results. And then they propose that that works a little bit like quantum teleportation, and in effect takes the information, the sort of details of the machine that's fallen in here, and feeds that information out through this kind of zigzag path. This is what they themselves say. In the process of black hole evaporation, particles are created in correlated pairs, with one falling into the black hole and the other radiating to infinity. The correlations remain even when the particles are widely separated. The final state boundary condition at the black hole singularity acts like a measurement that collapses a state into the one associated with the infalling matter. This transfers the information to the outgoing Hawking radiation in a process similar to quantum teleportation. So that's the proposal. The Cambridge physicist Malcolm Perry, writing about this a couple of years ago, has the diagram you see on the right here, and he describes it like this. He says it's the Penrose diagram of a black hole that evaporates completely, together with a river showing the expected flow of quantum information. The river is that zigzag structure. Perry says the interior of the black hole is therefore a strange place where one's classical notions of causality are violated. This does not matter as long as outside the black hole, such pathologies do not bother us. Our claim is going to be that such pathologies have actually been bothering us for almost a century, because entanglement is much the same thing. Only it doesn't need black holes. It needs something a lot more common, well, a lot more common around here than black holes. Okay, so that's the second ingredient, constraining a collider and connection across a constrained collider. Before we turn to the third and fourth ingredients, I want to get a bit closer to quantum mechanics in the sense that I want to make our toy example more structurally similar to a real Bell experiment. So let's call this quantum rock, paper, scissors. And the difference here is that as well as feeding their choice of rock, paper, or scissors to Colette, this time Alice and Bob each also toss a coin and send the result of that coin toss to Colette. So Colette gets 4 bits of information each time, 2 choices or settings, and 2 coin outcomes. And that's exactly the same amount of information recorded in each run of a Nobel Prize winning Bell experiment. And it's very easy for Colette to choose which results to keep, so that in the final results, the ones that she's kept, they look exactly like the results of a successful Bell experiment, showing the violation of the Bell inequalities. But of course, Colette's not going to win a Nobel Prize. There's no magic or non-locality here. It's just collider bias at work. She's produced the Bell correlations via this selection process. Now, we could imagine a version of this quantum rock, paper, scissors with a constrained collider relying on God or fate or lady luck or a super intelligent running a simulation, just as in the simpler version of the game. And this would have one interesting difference compared to the simpler version. In this case, the fact that we've now got outcomes as well as settings means that we can interpret the results as showing that Alice's choice of settings influences Bob's outcomes and vice versa. So the problem we had with allowing both of them free will in the simple version of the game would have disappeared in this more complicated version. But Colette obviously isn't still not going to win a Nobel Prize for this version, because nature isn't going to believe her story about God or fate, or they'll think, oh no, you're just throwing results away as you did before. Okay, now there's one other big difference between that quantum version of rock, paper, scissors and real Bell experiments, and that's that they're upside down with respect to each other in time. So in rock, paper, scissors, Alice and Bob are sending their results to Colette in the future. In real Bell experiments, the particles are coming from a source in the past and going to Alice and Bob. We'd now like to get rid of that difference too. So what we want is a version of quantum rock, paper, scissors, but with that orientation in time, that sort of V-shaped orientation in time. Well, we know how to start. Colette tosses the coin and sends the result. So Colette tosses 2 coins and sends the result to Alice and Bob. Colette is a pragmatist, so if she wants, she can change one or both coin results before she sends them to Alice and Bob. Can she produce Bell correlations? Well, no, because she doesn't know Alice and Bob's choice of settings. So she can't, for example, ensure that they get different coin results when they choose the same setting, as she would need to do to produce at least one sort of Bell correlation. But if we give Colette a crystal ball so that she can see Alice and Bob's settings in advance, it's easy for her to guarantee Bell correlation. So here's Colette with her crystal ball. It's a pity that the projected version of this is so disappointing. This is a beautiful piece of AI-generated artwork that I'm showing you there. The crystal ball means that Alice's choice and Bob's choice both feed into Colette's selection of outcomes here. And it's now easy for her to produce Bell correlations. The trick she needs is just to toss one coin and then to choose the outcome for the other coin based on the correlations that she's trying to emulate. So, for example, she might decide that she should send different coin results when Alice and Bob choose the same setting. Now a question. Does this version of the game produce a causal influence from Alice and Bob and vice versa? I see one person nodding. I say on the slide that a tempting answer is no. You might think, no, I don't, because it's just collider bias again. But there's one big difference, and that's the third ingredient. Colette isn't throwing anything away. She's simply choosing the results she wants using her ordinary ability to control the initial conditions of the experiment. Let's call this ability initial control. It allows ordinary humans with no supernatural powers to constrain a V-shaped collider like the one in this V-shaped version of the rock, paper, scissors game. And constrained colliders produce connection across a constrained collider, CCC. That's what we discovered at step 2. Well, does this mean that Colette is going to get a trip to Stockholm? There's real causation or quasi-causation from Alice to Bob and vice versa. And it doesn't need any relativity challenging magic because it simply goes by, well, I haven't actually told you that the crystal balls don't challenge relativity, but let's assume that. So Colette's Swedish prospects would be looking good if she didn't have to rely on another form of magic in the form of the crystal balls. If only there was something on the shelf in physics that would do the same job. Well, that brings us to our fourth ingredient, retrocausality. This is a picture of Louis de Broglie, famous French quantum physicist, and a graduate student of his in the late 40s. I don't know when this picture was taken, probably around about 1950. His graduate student was called Olivier Costa de Beauregard. And in the late 40s, when he was still a graduate student, Costa de Beauregard came up with an objection to the EPR Schrodinger argument we had at the beginning. He pointed out that Alice's measurement could affect things on Bob's side of the experiment without magical action at a distance if the influence took a zigzag path via the past light cones. Here's Costa de Beauregard later in life explaining this idea of zigzag. I don't know if you can see in the picture projected here, but there are arrows on the lines here. There's an arrow that goes there and an arrow that goes there. That's where how the causal influence is supposed to go in this proposal. Costa de Beauregard had this idea as I said, in the 1940s, but de Broglie didn't let him publish it. He thought it was too weird until 1953, after Feynman had suggested that positrons might be electrons zigzagging backwards in time. At that point, de Broglie said, well, look, this young American has published this crazy idea. Why don't you publish yours too? And after Bell's work in the 1960s, Costa de Beauregard always maintained that his zigzag would do the same work there, explaining the Bell correlations without any relativity challenging non-locality. There's a terminological note that we need at this point, where here's a quote from an email that an experimentalist, a quantum experimentalist, quite a well-known one, once sent to me. He said, for me, the Costa de Beauregard zigzag in space-time, which you seem to consider equivalent to retrocausation, is nothing else than non-locality. The addition of one time-like vector to the past and one time-like vector to the future, connecting the detections, results in a space-like vector, and a causal relation between the two ends, space-like separated, amounts to a non-local relation. Well, at one level, this person is obviously right. I can't tell you who it is because I don't have permission to quote from the email, but I can give you a hint. It's one of those three people. At one level, they're obviously right. The net result of Costa de Beauregard's Zig Zag, as Costa de Beauregard himself appreciated, the net result was a space-like causal relation. But it's achieved by combining two time-like causal relations, and so it doesn't challenge relativity in the same way. So I think what this person is missing is the distinction between a direct space-like connection, which is in tension with relativity, and an indirect connection composed of components compatible with relativity. But the terminological point is we have to be careful about how we use the term non-locality here. We could use it in the general way, in the way that this person is using it, so there's still non-locality. But then, of course, not all non-locality is bad in the same way, because the indirect kind doesn't challenge relativity. But we could restrict the term non-locality so that it was equivalent to Schrodinger's magic, so it was direct space-like connection. And in that case, this person is wrong. There isn't a right or wrong answer, it's just a terminological choice. But we need to be clear that the terminological choice is there to avoid tripping up on this point. And so the latter thing, the indirect connection, is what Costa de Beauregard Zig Zag would offer if it could be implemented in some real quantum model. And I don't think Costa de Beauregard himself ever actually proposed a model which might do this. I think in some ways he wasn't a particularly good advocate for the view. But clearly the idea was retrocausation. So the first part of the zigzag is a causal arrow going backwards in time. That's causation working backwards. And there have been some quite famous quantum retrocausalists since that time. This is a picture from a physics conference, I think in Poland in 1962. I like to think that the participants were making an attempt on the world record for the number of theoretical physicists you could stuff inside a VW. Right. But that aside, there are, perhaps remarkably, there are two famous quantum retrocausalists in this picture. So the man with his feet on the ground facing us, leaning on the car, with his hands crossed in front of him, that's Dennis Sharma, who was a very influential British physicist, influential particularly because he trained a remarkable generation of people, including Stephen Hawking, Martin Rees, David Deutsch, and many others. And he has a rather obscure piece in the 1950s in which he proposes a retrocausal version of quantum mechanics. Dennis Sharma was also a big influence on the man standing on the car next to him, who's Roger Penrose. And Penrose has long been, perhaps I should say, a quiet advocate of retrocausality. In some recent pieces, he's very explicit about it. But it goes back a long way, and there's a story from the 1990s of a meeting on quantum theory at the Royal Society in London. Penrose drawing zigzags on the whiteboard and saying, I can get away with suggesting this kind of thing because I'm already a fellow here. So that's two famous retrocausalists. And there's another one in this picture, unfortunately not the man on the right. It would be very much easier to defend the view if it were him. But the man on the left there is the Israeli physicist Mikhail Aronov, who has been interested in these ideas at least since the 1960s. There's a famous paper by Aronov, Bergman, and Leibovitz, the ABL paper from 1964. Now, I don't know if at that time Aronov thought of it in a retrocausal way, but certainly more recently he clearly does. And there's a whole group working around him in Israel who all have what I think of as retrocausal views. Those are some famous ones. Here's some less famous ones. Well, there's Ken and me This is a piece that we published in the Conversation a couple of months back, which has been read more than 80,000 times. Maybe I could promote us to famous retrocausalists now. This is the abstract from a piece by Matt Leifer and Matt Pusey from a few years ago, a piece in which they generalize an argument that I published a few years ago, showing that under certain assumptions, time symmetry in quantum mechanics requires retrocausality for reasons which are not present in classical physics. Leifer and Pusey produced a more general version of this argument, showing, as I say at the end here, the impossibility of a non-retrocausal time-symmetric ontology. Now, there's a lot more to say here. There are controversial issues about the definition of time symmetry. We won't have time to go into those. One of the more recent advocates of the view is Emily Adlam, who you see up here on the right. She has a number of interesting pieces, and this is something which is on YouTube from a couple of years ago, a talk called Retrocausality to the Rescue. Okay, so in sum, there's plenty of retrocausality already on the shelf in quantum mechanics. And so I can now explain our recipe. Retrocausality introduces colliders into Bell experiments, causal arrows that run backwards to the source at which the pair of particles is produced. That's interesting because colliders produce collider bias and causal artifact correlations that look like they involve causation, but really don't. But constraining a collider can turn a causal artifact into a real connection across a collider. Again, I'm being silent on the question as to whether it's real causation, but it's certainly something more than we have when the collider is not constrained. And in the case of colliders in the past, constraint is often easy. It just follows from normal initial control of experiments. So that's the recipe. 4 simple steps, all of them, as I said, available on the shelf. This recipe shows that it's easy, in principle, to produce the kind of correlations that are characteristic of entanglement, Bell correlations, once we have the 4 ingredients. Now, it's obviously a further big step to show that this is how entanglement actually arises in quantum mechanics. That would require looking at particular models and at the kind of ontologies and variables and probabilities that they provide. We're not claiming to have done that. But as far as we know, there aren't any competing hypotheses that propose an explanation for entanglement in simple pre-quantum components in this way. So we call this the E equals CCC hypothesis. Entanglement equals connection across a constrained collider. Entanglement is connection across retrocausal colliders constrained by initial control. And so what we're proposing is that once you have the combination of retrocausality and initial control, which obviously we have anyway, entanglement is something you should expect to emerge from your picture. And if this proposal works, what it does is in effect explain something that I think Costa de Beauregard himself never explained. So he'd introduced this idea of causation working backwards, but I don't think he ever explained how you get from 2 causes working backwards to zigzag causation. And I think this recipe explains that. It shows how nature can build a zigzag connection from the 2 backward-facing zigs provided by retrocausal models of Bell experiments. If it works, it's a novel kind of quasi-causality produced by a constrained collider. And if it works, I think it means that we now have 3 basic arguments in favor of retrocausal models in quantum theory. So there are three tracks which all lead to retrocausality. First of them is the one that Beauregard himself was clearly advocating. It's a way of preserving, it's a way of avoiding non-locality, avoiding Schrodinger's magic, and explaining EPR Bell results in a way which is obviously not in tension with relativity. Then there are the appeals to time symmetry, based on my argument in the generalization by Leaf and Pusey. As I said, I didn't go into that at all, but that's a distinct kind of argument, I think. And then if this proposal works, there'll be a new kind of argument, and it's going to be an argument which will appeal to what philosophers of science call argument to best explanation. Because if it's the case that this offers us an explanation of entanglement, the weirdest feature of quantum mechanics, and nothing else does, then that looks like a pretty good case for invoking argument to best explanation, and saying that that means that the hypothesis on which this hypothesis depends, namely that there's retrocausation in cases of entanglement, is true. So I think unless there's some problem with this hypothesis that we haven't spotted, we now have three kinds of arguments for taking retrocausality seriously in the quantum world. Okay, just to finish up then, how are we doing on time? 3 minutes, good. Perfect. A little bit of counterfactual history. I think we can now see that Bell's results offered us a choice like that. This picture might look like it's AI generated, but it's not. I found this in Switzerland somewhere. So in the face of Bell's result, there are two ways we could go. If we wanted to keep Einstein happy, what we needed to do was to go to the left and pick up on Beauregard's suggestion that there's zigzag causation in EPR Bell experiments. But of course, Bell himself didn't go that way. He went the other way, the way which produces a tension, or at least an apparent tension, with relativity. And most people have followed him. This is just a generic picture of a crowd of physicists that I found on the web. I'm not claiming that these individuals in particular have made this decision. Okay, so the question I want to raise then is the question, why was it so overwhelmingly in this direction? Why didn't more people explore going left? And I think part of the answer, I think this is quite a complicated sort of historical sociological question, but part of the answer emerges if we look at the way in which Bell himself and other people responding to Bell discuss the issue of causality in the context of EPR Bell experiments. So this is a diagram, as many of you will know, it's a diagram stolen from some of Bell's own writing. He often uses diagrams like this. I've just added the space-time axes and the labels here. And it's a kind of space-time diagram of what we now call a Bell experiment. And Bell's argument assumes that the measurement settings, little a and little b here, are statistically independent of any pre-existing hidden variables represented by lambda. Now, as Bell noted, that could fail if both a and b and lambda are controlled by something else, by a common cause, as causal modelers say. And that's the option which has come to be called superdeterminism. I think Bell himself was the first person to use that term in this passage. So this is from an exchange in 1976 when he was responding to a short piece by Shimoni and Clauser and Horn. Bell says, an essential element in the reasoning here is that A and B are free variables. One can envisage then theories in which there are no free variables for the polarizer angles to be coupled to. In such superdeterministic theories, the apparent free will of the experimenter and any other apparent randomness would be illusory. So this is my representation of what Bell has in mind, I think. So there's something which controls the Alice's choice of measurement setting and Bob's choice as well, that also controls the hidden variables. And so Alice is not actually free to vary the measurement setting independently. And this is the presentation of the same idea by Shimoni, Clauser, and Horn in the same exchange. They say in any scientific experiment in which two or more variables are supposed to be randomly selected, one can always conjecture that some factor in the overlap of the backwards light cones, that's the thing I put in here, has controlled the presumably random choices. But skepticism of this sort will essentially dismiss all results of scientific experimentation, unless we proceed under the assumption that hidden conspiracies of this sort do not occur. We've abandoned in advance the whole enterprise of discovering the laws of nature by experimentation. And I think they're basically right about that. And it's a point that you could give perhaps a somewhat more precise formulation in terms of causal model. The whole causal modeling framework assumes, and this is the thing that people like Judea Pearl and Jim Woodward and others who write about these ideas are very clear about, it assumes that we can reach into the model from the outside and control the value of the so-called exogenous variables, the variables that we can intervene on. And in this kind of picture, there are no intervention variables because the measurement settings are being treated as controlled by something in the past. So it's a view which is deeply in tension with the whole business of causal modeling, of discovering the causal structure of the world. But there's another way that the measurement setting A can fail to be independent of a hidden variable lambda, namely if A is a cause of lambda. That's completely different from superdeterminism. But I think that many people, including at least at some stages, Bell himself, have confused the two. I mean, even very recently, it's easy to find examples of leading people who are in fact running these two possibilities together under the heading of the so-called free will objection. But this possibility is completely compatible with free intervention on the measurement settings. We can still treat measurement settings as intervention variables. And it was on the table from the beginning, or almost from the beginning. Certainly in the context of this discussion in 1976, Costa de Beauregard himself contributed a comment on this discussion. So why did almost nobody explore that option? This was the situation, which was, of course, clearly apparent to people like Bell himself. This way, this is supposed to be red, indicating, no, don't go that way. And that's supposed to be green. Go left, no apparent conflict with relativity. Go right, apparent conflict with relativity. Now, of course, as I said at the beginning, maybe there's a way of dealing with that apparent conflict, and a huge amount of effort since then has gone into looking for ways. The effort I'll represent like this. But in comparison, very, very few people have explored the option of following Costa de Beauregard in exploring the retrocausal possibility. And I think there's a material for a lovely HPS thesis on that topic. Why did it take so long? Where are we now? 60 years since Bell's theory. And it still hasn't been explored properly. Okay, I'm going to leave you with that question. And another little historical question. I talked about the Parisian Zig Zag. It turns out that there are 2 Zig Zag cafes in Paris. And this one, which I think has been there for a long time, is right between the Sorbonne and the École Polytechnique. And so I'm pretty sure that Costa de Beauregard, he used to hang out in those parts. So I'm pretty sure he must have known about this cafe. So I'm wondering whether this cafe was the inspiration for his approach to quantum mechanics. I'm hoping that some HBS graduate student will solve that puzzle for me too, by at least finding out how long that's been there. But for now, I'll leave you with Costa de Beauregard, and that's it. Thank you.
Thank you very much, Hugh, for the great talk. And we'll now, as is our custom, take a 5-minute break for catching the breath, bathroom, and fixing the
Okay.
of an audio.
Okay, thank you.
Okay, I think we're all back and have some half an hour for the Q&A. So please raise your actual and or virtual hands, and I will start with the people from the room who are students of all levels, starting with you.
Yeah, thank you very much for the interesting talk. And I just have a question regarding the direction or the symmetry, asymmetry between Alice and Bob. So it seems like there's always the causation going on from Alice to Bob. So you're only looking at that direction, at least.
No, I wanted to go in both directions.
Okay.
And so one of the points I made about the modification to the rock paper scissors when I introduced the coin tosses, that enables us to say that in the constrained case, Alice's choice of setting is influencing Bob's coin toss results and vice versa. But no, you're absolutely right. The whole thing should be completely symmetric between Alice and Bob, except it's Alice who's winning and Bob who's losing, of course. That's just an artifact of the example.
Okay. So also in the Zig Zag example that you concluded, and where it says like Alice has somehow showing the way from Alice to Bob, so it's somehow retrocausal control over Bob. So it's always happening at the same time.
Yes, yes. Well, I don't have the slides now, but
I can bring them back for you if you want.
it would be helpful.
Yeah, of course.
Yeah,
sure. Presentation mode or?
No, I don't seem to be able to get that. Okay.
Yeah.
Okay, so on that one, I didn't bother to put in the arrow going the other direction. See there I've got the arrow going in both directions. So in that version of the game, Alice is affecting Bob's coin toss, and Bob is affecting Alice's coin toss. Once we have this constraint.
And no one is overimposed over the other, so it's like simultaneously. Simultaneous in that sense.
Sorry.
Both in the same sense, so there's nothing overimposed over the other.
Yeah, no, it's completely different, which is of course what you want in the quantum situation.
Okay, great, thanks.
Okay, Moritz.
Okay, thank you very much. I think it's basically a follow-up question. So I think in the original Zig Zag proposal, you have this unsymmetry, right? So how is the proposal right now with the collider different from this original proposal? And how is it also distinct from the superdeterministic case?
By the original proposal, do you mean Costa de Beauregard?
Yes, exactly.
No, I'm sure that Costa de Beauregard always thought of it in a symmetric way.
Okay. All right. So he also has like a causal instance from A to B and from B to A.
Yeah, no, I'm sure he would have just taken the symmetry there for granted.
Okay, and the superdeterministic case is different because you don't have the free choice from Alice and Bob, and in the retrocausal case, you have free choices, and that's what makes the difference for you.
Well, the difference is that there's a completely different causal structure. So the principle of the common cause tells us that where we have a correlation, there are two possible causal explanations for the correlation. One is that both of the variables are effects of a common cause. The other is that one is a cause of the other. And they in a causal diagram, they're completely different. And so that's the difference. So I think part of the answer to the historical question was that people just got mixed up. They didn't see that in addition to the superdeterministic option, there was also this retrocausal option. Yeah. Now, of course, they were assuming some sort of principle of causality, that causation only works forwards. So but why should they have assumed that in this context, where relativity was giving them such a good hint that it wasn't true?
Yeah, so then we had this question, like, do we then have to assume that it's simultaneous? Or can we assume that, do we have to assume a time order for these choices?
No, I mean,
or can it be like an A, B, before B, and can there still be this symmetric influence from A to B?
Yes, absolutely. Unlike in the standard, within the standard model, it makes a big difference whether Alice or Bob makes their choice of setting or does their measurement first, because that has the effect, whichever does it first collapses the wave function on the other side. And there already is the tension with relativity. I mean, of course, as you probably know, Einstein already thought, when Einstein complained about spooky action at distance, he was talking about the instantaneous nature of collapse. But in these EPR cases, in that point takes a particularly vivid form, because in the standard version, the time ordering matters. But once you move over to Costa de Beauregard's picture, the time order is completely irrelevant.
Okay, we will go with the order of Zag, then it's Sebastian Miller on Zoom, some pleasure, and please raise your hand again if I missed your question.
Hi, yeah, thanks so much for the lovely talk. So I see some intuitive appeal to this proposal or this hypothesis in its being on good terms with relativity. It seems like the way it's on good terms is that you have this locus of or the site of causality is now local, so the pairing side. Am I getting that right?
Yes, well, I mean, you've got the causal relation extends in space-time.
Okay,
but the connections all stay within light curve.
Within light curve, okay. Now, there's one principle akin to locality that you hadn't considered, and I want to throw in the mix because I think it complicates the roads picture, the two roads. That was a really funny picture, by the way. On that. And for me, it spoils some of the appeal of this, and it makes me feel like there's another option that's much closer to standard quantum theory and non-local in the sense that people think of quantum theory of, and that's separability from Don Howard. So Howard, in looking at the EPR paper, I'm sure you're familiar, he identified two principles here. You need to show that these two spatially separated systems or postulate they have their separate reality. They're factorizable, as so to specify the total reality is just the mereological sum of all the realities of the different spatially separated regions at a given time. And then on top of that, no faster than light signaling. Now, it seems to me like this retrocausality picture hypothesis that you have whatever the details we say, that retrocausality has to be non-separable.
Yeah, right.
Now, in the sense that, it's not just that detector B is retrocausally determining something at the preparing site, but it's, as it were, determining this property and this other property together with this retrocausal influence from A, detector A. And both of those are spread out through the whole space-time, you're saying, yeah?
Yeah.
Okay, now, it seems to me, another option here is just to reverse the arrow of causality to say it's forward-looking, non-separable causality. So that at the preparing site, you have forward-looking causal arrows going in both directions that are non-separably determining measurement outcomes, but also locally. So it's not as though there's passive light signaling, it's just that this causality is forward-looking, non-separable. So do you see any problems with that proposal? And if not, is there anything you can say to motivate yours as superior?
Yes, I mean, I can't give you all the details, but this is the way I hope it will go. I hope that one thing that will fall out of this will be an explanation of non-separability. And the way I think it will go is like this. Whenever we're considering causal intervention in the world, we're in effect dividing the world up into two regions. There's the stuff we can consider to be fixed in advance of our intervention, in advance of any decision we make about what to do. And there's stuff that we have to hold open until we've made that decision. I think that distinction between fixed and open is a very basic feature of an agent's point of view, and it's really responsible for the intuitive asymmetry between past and future. Now, the possibility that's on the table, once we allow the possibility of retrocausality, is that distinction between fixed and open doesn't line up neatly in any way with the sort of distinction between past and future. In particular, retrocausality means that some stuff in the past is going to have to go on the open side too. And then once you've got this story about connecting across the collider, it explains why some remote stuff has to go in the open category as well. And I think that's what non-separability will turn out to be. So if it works, I think this will give us an explanation for non-separability and avoid having to treat it as sort of primitive in the way that I think your proposal would have to be.
Yeah,
If it's brief.
yeah. So I guess this is a longer conversation and have it work on here. So, but I'm struggling to see how it couldn't be primitive. It seems like your picture has to be something like the initial conditions end up being settled in this non-separable way, pending, as it were, with the forward conditions in the future of the detector settings, that the detector settings are jointly retrocausally determining the properties that then thereby become revealed.
Well, once you've got retrocausality in the picture, you've got to be very careful about treating the initial conditions as settled. Because the initial condition are going to be some other stuff that's up again. And independently of quantum stuff, that's already a proposal.
Determined in this retrocausal way, in a joint retrocausal. Determined. It would have to be jointly depending, just based on the statistics of the measurement outcome.
Yeah, but I don't think it's going to have to be explained as a primitive. I mean, invoked as a primitive. It will be explained in terms of retrocausality, plus the fact that you've got more than one agent in the picture. I suspect you can find a corresponding thing in the future just from an ordinary notion. You probably look at colliders to do it. But as you say, it's a longer conversation.
Great, thank you. Could you go back to the slide that had the quotes that you could tell us who of the three?
Yes, now let's see. I think that was forward, wasn't it?
Yeah. So I found this pretty confusing because I thought, well, I mean, even talking about vectors doesn't seem to be the right way of thinking about it, right? Because I mean, the vectors live in the tangent space. The question should be, is there a curve in space-time that connects B and A and that goes backwards in time, right? And then there is no such equivalence. Then there's one curve that should connect the two of them.
Well, I mean, of course, it would be nice if there was a simpler objection to this,
Yeah.
my terminological point. But I imagine what this person is thinking. They're thinking of vector in some more informal sense. So they're thinking vector in something like a causal arrow sense. And then this was the diagram that we saw in Costa Bergson Blackboard.
Yeah.
And you know, something like this. And I think this person who can say that the sum of these two causal arrows gives you a resultant causal arrow. I think that's all we need.
Which is true, but then I would say, well, that speaks possibly against that picture, right? I mean, if I'm asking, is there a causal influence from B to A that goes backwards in time? Yeah. Or then I'm asking about the curve connecting that, right? I'm asking about an actual path that a causal signal, a causal influence could take.
Well, I mean, what I would say, I mean, I'm sort of, you know, I want to go in that direction.
Yeah.
But I think sort of arguing on that person's behalf, the retrocausation is actually here. It's from B to C.
Yeah, fair enough.
And also from B to C.
Yeah.
Yeah,
but I think the point stands that there is a total curve that connects B and A via C, which contains, you know, which goes.
Well, of course, yeah, as I say, that's what I want to say.
Yeah.
Yeah. But nevertheless, this terminological point does trip people up.
Okay. And I had directly connected to that. I had another question, but it might not be. Well, I'm not sure. It's okay. So I can see how by introducing retrocausality you avoid a conflict with special relativity. But I wonder whether you get a conflict with general relativity, in that, right, depending on which space-time you're looking at, this type of, you know, if you have a time-oriented space-time, then you shouldn't be able to go backward in time, right? And even if, to the extent that time travel is allowed, it's typically via close time-like curves, which that wouldn't be. So I wonder how.
Okay, that's an interesting question that I haven't come across before. Although my intuition is to say that if you think it's a problem, you're probably taking too seriously the notion of time orientability or connecting it too closely to the notion of causation. Now, of course, there is a tradition in relativity theory of doing that very, very closely.
Yeah.
Indeed, for some people, causality is the fundamental notion. But we're a long way away from that.
I see. You could say, well, this is the same sort of mistake that has been done in this discussions, namely that temporal order and causal connections should be should go hand in hand, and they should be kept apart.
Yeah, they should be kept apart, and they should, in my view, it's not really a strictly required view. They should both be deflated.
Right.
So we should think there is no fundamental temporal direction.
Right.
And we should think that the causal direction mainly comes from us. It's mainly our asymmetric temporal perspective as agents. But that leaves open the possibility that as agents we might discover that some of our interventions wiggle things in the past as well, in subtle ways. And that's what I think is going on in the quantum field.
Okay, great. Thank you.
Maybe let's have a question by Sebastian Miller on Zoom, then two more questions from Zoom. And again, let me know if I missed your hand. Sebastian, please go ahead.
Thanks, maybe I can start. So basically, typically the construction of like quantum theory, you start with a state space and then time translate it to get basically the time evolution that you want. As far as I understand, you put the entanglement into the time translation. Typically, just put into like the state space.
I'm sorry, I didn't understand that. It's partly that I'm having trouble hearing you, but also partly I'm not understanding the technical point, I think.
So I will try to be prominent. So you typically in like the construction of a quantum theory, you start with a state space and then time translated to like a later point in time. And typically like the entanglement is put into the state space. So you start with an already entangled state and then like you time translate it to a later point in time and do something with it. But like as far as I understood you put the entanglement into the time translation, right?
Well, perhaps it would be helpful if I said that everything I'm doing here is pre-quantum. So what I'm showing is that from pre-quantum ingredients, the 4 ingredients in the recipe, it's easy to produce correlations that look like Bell correlations. Now, as I said, it's then a further big step to show that this is how entanglement actually arises in quantum theory, and that's going to require looking at particular models. And in particular, it's going to involve considering the kinds of issues that I think you're raising. But I think I'm going to dodge the question by saying that for the purposes of what I talked about here, it's not really relevant, because the central point is you can get something that looks like the kind of correlations that we associate with entanglement from these ingredients.
Sam, maybe I think this should just work fine for us.
I just do it here. Thanks, you. In principle, we would want the physics to tell us what the direction of the causal arrows is. I guess you don't agree with that.
No.
Okay, because my question was going to be, where in the model does that come from? So could you then say a little bit more about,
Yes.
if the physics doesn't determine it, how you see the matter?
Yeah, absolutely. I'd be delighted to do that. I just put on my pragmatist hat and take a drink of water. So my view is, as I sort of alluded to in my answer to Dennis, my view about the direction of causation, and indeed about the direction of time, is a thoroughly pragmatist one. So I think there's no fundamental direction of causality in reality. In reality, but our causal concepts are very closely tied to the perspective we have as agents. And as agents, it's a sort of contingent feature about all of us that we all have the same orientation in time. So when we're thinking about, when we're thinking causally, we're thinking about, well, if I do A, what will happen? And the time order is already built in there. And one way I like to develop that point is to say, well, we now have good physical ways for thinking about the possibility that there might be creatures elsewhere in the universe who have the opposite temporal orientation, because the thermodynamic arrow has an opposite direction in some parts of the universe. Creatures in that region would plausibly think of the future and the direction of causation as being in the opposite direction from us. And just like up and down, there's no fact of the matter as to who's right. So that's my general line on both the direction of time and the direction of causation. It's completely non-fundamental. But then the interesting thing, which is relevant here, is that perspective doesn't seem to enforce a sharp past-future asymmetry on causation. You can think of these sort of hybrid cases where we can do something in our immediate future, like choosing a measurement setting, where because of the correlations built into the model that we're looking at, that actually makes a difference in the past as well.
Right. Do you mind if I?
Yeah, no, go ahead.
Sure. Is there something then about our particular perspective? What about our particular perspective makes it so that we adopt one causal direction rather than another? It seems to me that when it comes to the causal models, which direction, if you just take the absolute simplest, where you just have two nodes and one arrow in between them, that even in the simplest case like that, there is a difference about what happens when we intervene on the one versus the other. So in terms of the predicted statistics for the outcomes, right? So what about our perspective determines those arrows such that it makes a difference to these sorts of things?
Well, let's see. I don't know if this will be helpful, but in a couple of recent things, where I've been trying to make this point about the direction of causation coming from our perspective as agents, I've thought of simple kind of Humean regularities and about how we determine which way the causal arrow goes. And we have a regularity between, we say A's are typically followed by B's. Let's see if I can reconstruct one of my examples. So I imagined a correlation, a Humean constant conjunction that we notice in a university cafeteria. We notice that dropping plates on the floor is typically followed by mess on the floor. Is that causal? And if so, in which direction? Well, what we do is we want to find out whether A causes B and whether B causes A, whether both or neither. What we do is we imagine intervening to produce A or B. Now, if we imagine ourselves intervening to produce a drop plate, then it's easy. We just imagine ourselves dropping a plate. And then we see a mess on the floor. Okay, that counts as causal because when we intervene, the correlation is still there. Now, we want to try intervening on mess on the floor. So we think, well, let's make a mess on the floor. We make a mess on the floor. Has somebody dropped a plate in the past? No, in the past of this mess on the floor is whatever we did to produce the mess on the floor. So we put ourselves into the picture in the immediate past of the variable that we're considering intervening. So that's where the asymmetry gets in. And creatures who had the opposite time direction would put themselves into the picture in the future, not in the past, as we would say. And we can do that in toy cases because we can imagine, imagine the perspective of a novelist who wants a certain thing to happen at a certain point in the novel. So they can fix something in the future in that way, and then, as it were, run the story back. But for us, we're always intervening from the past into the future.
There's more to talk about.
No, it's a big issue, but
yeah.
But that's the basic idea.
Yeah. Is this a new question or a follow-up? I'll. Yeah. Go for it, and we'll have 2 questions from the.
Thank you for a nice talk. I have a question. Are there already sensible bounds for this on this retrocausality? Because when I just look at what they compute for the Bell experiments, the average they compute, you can also construct averages which far exceeds the quantum bound you would get. So I would expect that for this retrocausation, there should also be severe constraints on.
Yeah, that's a very nice. That's a very nice question. Now, you might say, well, look, it's got to be a consistency constraint that it can't be used as signal. Because if you could use it as signal, then you get the usual sort of causal paradoxes. So one question you could ask is, can you extract the quantum bounds from a no signaling condition? Now, I think on the face of it, you can't do that because there are stronger, there are stronger models which also seem to have no signaling. I was talking about this to somebody in Toronto last week, and I can't remember who it is, but they sort of suggested some other line of work. I'm sorry, I can't remember what that was, but it's a really good question. And I think one of the interesting parts of it is whether I mean, it's the kind of question that people ask about quantum theory anyway, of course. So one of the really interesting questions from my point of view is whether adding retrocausality makes it in any way easier to come up with the quantum band. So I don't know the answer, but no. If you have any thoughts, let me know.
We still have time for two questions from Zoom. So first by David, then by Jorn.
So thank you very much. This is a question by Jean Pijnenburg, but also on behalf of David. Well, it's not a question. We just want to say that we thoroughly enjoyed this talk. It was a real pleasure. And we have the impression that a lot has happened since the paper with Ken Wharton was published in Foundations of Physics. And I was wondering, and perhaps you too, David, can we expect a follow-up on that particular paper in Foundations of Physics, or perhaps even not a paper, but a book?
Well, I don't think you can expect a book. As you'll know, if you've looked at the paper and the version on the archive, this idea actually emerges from something which is in the appendix of the latest version on the archive, but not in the published piece. And Ken and I wrote it up. We were prompted by the Nobel Prize results last year. We thought, oh, that's a good hook to hang a more popular presentation of this idea on. And so we started to write one, and some descendant of this piece, the popular piece, will appear in Eon at some point.
Oh, in Eon. Oh, that's good.
Yeah.
Well, thank you. I'm looking forward to that one.
I'll let you know, Jean.
Thank you very much, Hugh. It was a really and extremely enjoyable. Thanks.
It's lovely to have you two in the audience.
Yeah, well, it's lovely to see and hear you again. You're making progress after progress.
Jorn, please go ahead.
Thank you, and thank you for a really interesting talk. This is a sort of a follow-up from the point about the Serelson bound in quantum mechanics, or general quantum mechanical bounds. I would say that I'm quite fond of the retrocausal option in to Bell's theorem. It seems like a quite elegant solution. Maybe my main reason to still be a bit skeptical is how much quantum mechanics are we able to get out of it? To what extent would we be able to reproduce some of the quantum mechanical, or the quantum mechanical predictions follow naturally from assuming retrocausation? Because it seems to me that for quite a lot of the options that are on the table, like the two vector space formalism or the transactional interpretation, they are somewhat like formulating or taking the quantum mechanical formalism and just giving it the causal interpretation, which doesn't seem to be in the spirit of the sort of attempt to try to reconstruct quantum mechanics from and maybe a new vision about how we can consider reality.
Okay, no, I think I completely agree with you that some of the approaches to build retrocausal models, including the so-called transactional interpretation and the Aronov's two-boundary condition approach, they seem to me to be going in the wrong direction. I mean, it seems to me that the big attraction of a retrocausal approach is that it keeps open the possibility of a so-called psi-epistemic view of the wave function. You don't need all that. You don't need all that massive ontology in the wave function, let alone in the Everettian version of it, because you simply treat most of it as epistemic. And it seemed to me from the beginning, when I first started thinking about this 50 years ago or so now, that, of course, I was already convinced rightly of the block universe view. The world, as it were, knew what the measurement in the future was, why should it bother to carry around that vast load of ontology whose only job was to prepare for a future which was never going to happen? If this approach works, I think it will be in terms of an ontology which is in some ways much simpler, because it's a hidden variable model which is treating a lot of the usual quantum formalism as purely epistemic. I don't have a model to offer myself, but my collaborator Ken Wharton is trying to formulate general models. I mean, he has less general models as other people do, but he's trying to formulate a general model which will handle basically an entire class of partially entangled states. He says he's not quite there yet, but watch that space.
Thank you.
Yeah, thank you. I think that's a perfect ending. So please join me in thanking you again for the great talk.
Yeah, well, thanks to everyone on Zoom and here for